Alrighty, let's finish up our chapter 13 with infinite geometric series, which is the sum of a geometric sequence that has an infinite amount of terms. Now, you might be thinking, if you add up an infinite amount of terms, won't the sum just always be infinity? Sometimes it's infinity, but other times, which is what this section is focused on, is that it will actually add up to be a regular number. So let's take a look. Here in the book, let's just jump down to the formula. Actually, let's not do that. Let's first talk about the difference here. Okay, so here is a geometric sequence. Let's start with a really basic one, like one. Actually, I'll do a series. We'll just add them up, right? Okay, so what's happening here? This is a geometric sequence. The ratio between each term is 2, and we're adding up all the terms, and it's going on forever. And so if we do this, what's that going to be? Well, we're just going to keep adding larger and larger numbers, right? This is infinity. There's nothing we can do with that, okay? So we're not focusing on that in this section. What we can do is, suppose I give you a sequence like this. So now, notice what's happening. Okay, we're going to go on forever. So this is a sequence that starts at 32, and the common ratio is 1/2, because we're multiplying by 1/2 each time. So obviously, as I start adding up these numbers, the value is going to grow. But at some point, because this goes on forever, right? At some point, the amount that I'm adding is getting closer and closer to 0. And so I'm adding such a small value that in the long run, it doesn't even make a difference anymore, right? So it's what we call an infinitesimally small value. So the idea here is that this will converge to some number, okay, some value. And that's what we call it converges. So it converges to some value. And that's what we're going to learn how to do. So the formula, as we can see here in the book, the formula will be using sigma notation, infinite sum, right? Here would be the example of the function. And then this is the formula. And it's actually a very simple formula. A over 1 minus r. And a is the first term, right, by plugging whatever this is into the function, and then dividing by 1 minus the ratio, so the ratio between each term. So because I put this example here, let's go ahead and find out what this sum value actually is. What do we actually get with this example I used? Well, our first term's 32. And then 1 minus, what's the ratio? What's the multiplier? What am I multiplying by each time? Multiplier is 1/2. And so that's 32 divided by 1/2, right? 32 divided by 0.5 or 1/2, which is 64. And so now let's get rid of that. Let's put that equals 64. Because if I add up all of these numbers, including all of the little infinitesimally small numbers, it converges to the value 64. It gets closer and closer and closer to 64. And because we're talking about an infinite sum, we say that that sum is 64. So that's how we use this formula, and that's basically what we're talking about in this section. That's the main part, okay? So the idea here is that it will converge when the absolute value of the ratio is less than 1, okay? Or in other words, when we have exponential decay. Exponential decay. Okay, because then we're adding that smaller and smaller value on as we get the term number off to infinity. So let's take a look at we're not going to do actually everything in this section. Let me just let's just do something else. So the next thing I want to talk about is the idea of a repeating decimal. So if I give you this number, 0.3 repeating, I think you all know what this number is as a fraction. I think I can safely say that this is equal to 1/3. Nobody would contest me on that, right? I think you would all agree with that. But as soon as I say 0.9 repeating is equal to 1, well, then people start to contest me with that, right? They say, well, that doesn't really make sense to me. So let's take a look at this idea. Let's first take a look at this one that we all agree with. So what does 0.3 repeating look like? If I write a couple more 3's out there, we can see that this is the same as if I take this first decimal, right, 0.3, and then I add, the next one is in the hundredths place, right? So that would be 0.03. Because if I add these two first terms together, I get the 0.33, right? I get these first two. And now I will add 0.003, and that'll get me to here, right? And you're going to see what I'm going to do here. I'm just going to continue that on forever. And that will give me this. Okay, so then what we have here is an infinite geometric series. So how do we express this as a function, as a sum? So using sigma notation, it's an infinite sum, and my first term is 0.3. And what's my ratio? What am I multiplying on this side here between each term? I'm multiplying by 1/10 or 0.1, however you want to look at that. So that's the equation, right? That's the function there. That's how I express this. And so now I can just use the formula of a over 1 minus r and say, okay, well, the 0.3 is my first term, and the r is 1/10, so 1 minus 1/10. And that's 0.3 over, what's 1 minus 0.1? 0.9. And so 0.3 over 0.9 reduces to 1/3. Okay, and so we see that that's how that works. So if I do the same idea with this, I get that's 0.9 plus 0.09 plus 0.009, and so on. So that's the sum from 0 to infinity of 0.9 times 1/10 raised to the n. So what's the first term? 0.9 divided by 1 minus, what's the ratio here? 1/10. So that's 0.9 divided by, what's 1 minus 1/10? 0.9. And what's 0.9 divided by 0.9? 1. And so we see that 0.9 repeating is equal to 1. So we can actually use this idea to turn any repeating decimal into a fraction. So, because if you remember from rational and irrational numbers, a repeating decimal is a rational number, which means it can be turned into a fraction. So if I just make one up, let's just make one up. Let's say it's 4.382 and 82 repeats, right? So 4.382828282. Yeah. Okay. How are we going to represent this as a fraction? Well, what we want to do, just like we did up here, we want to represent the repeating part as an infinite geometric series. The other part just kind of stands off by itself. So what I'm going to do is I'm going to say that this number is equal to 4.3 plus 0.082. Okay, that would give me just this number without repeating sign, right? But because there's a repeating sign, I have to say, okay, plus point, and now I have to fill in the zeros from what I currently have. So I need 1, 2, 3 zeros, and then put on another 82, right? Because that'll just kind of fill in the spaces. And then that's going to go on forever. Okay, so what does this become? Well, this 4.3 is just 4.3 plus, and now this is the part, because this is the repeating part, this is the part that I can write as my infinite sum. So I'm going to take the first part of this as my first term, and then I'm going to have to figure out what my multiplier is. So my multiplier is, well, how many times am I moving the decimal? Moving the decimal twice, right? So that's 1 over 100. Okay? If I was moving it 3 times, it would be 1/1000th. If you move it once, it's 1/10, right? It's that idea of just multiplying by 1/10 or dividing by 10, dividing by 100, whatever it may be. So there's the idea there, okay? So now we can just do, okay, well, that's still just 4.3, but now this sum becomes 0.082 over 1 minus 1/100th. And so that's 0.082 over 0.99. With a 4.3 in there, sorry. That 4.3 is still there in front. Okay, so now we can just divide this. And so if I bring up the calculator, I'm going to want a fraction as my answer. So I'm going to go to mode, and I'm going to want my answers to be exact. And okay, well, I don't know where that is on this. I'm used to a different calculator. Okay, never mind. So let's do 0.082 divided by 0.99, and let's make it a fraction. It's 41 over 495. And now this, we know, is just 43 over 10. And now we just have two fractions that we add together, find common denominators, add them together, right? So plus 43 . Let's make that a fraction. So alpha y equals, enter, 43 tenths. Because usually if you use fractions, it will give you your answer in fractions. And there's our final answer, right? I just kind of made up this number, so we ended up with this not very nice looking fraction, but it is a fraction of integers, which kind of proves and shows that this repeating decimal, 4.382 repeating, can be represented as a fraction and therefore is a rational number. Right, so it's just another way of applying this infinite geometric series to sort of like number theory type work. So yeah, that's about it. So the idea here, remember, is we have our formula. Okay. There's our formula. That's what we're definitely going to want to know. And then remember that it's only going to work, basically. It's only going to converge when the R value is less than 1. So we can only do this when R value is less than 1. If R value is not less than 1, then it's going to be an idea like this where it goes off to infinity. Okay? So that is infinite geometric series. And that's it for chapter 13. So I will see you guys next time. All right.